I have an example on the board of the NASA X-57. There's a lot of published works on this aircraft. But if we boil it down to a very simple level, it's a battery pack, one or more inverters, one or more electric machines. In this instance, we have 2 drive machines and 12 smaller lift machines. So you have a very high level of complexity at the aircraft level. And then to add something interesting to it, that rotating shaft is creating a torque and a speed to spin a propeller. And this propeller has its own inherent efficiencies, optimal operating points. And we want this whole battery to propeller drivetrain to be as efficient as possible because this battery range is very limited, especially with the high power demands of aircraft. So people are going to look at individual components, but also the full system. And if we can optimize a full system, we can really make our aircraft have as long of a range as possible. So with that, we need a test stand. We're here to talk about testing. So if we take this novel approach and we think about what we saw on the first slide, we can start assembling a test stand in our heads. So this is an example of a very interesting test stand for doing a full electric propeller measurement. So we start with a base. We have a support column, a rigid stand, and then a load cell. Now, with the propeller, to get the propeller efficiency, we want force or thrust, as well as air movement. So for that purpose, we need a load cell to really get the full system efficiency. We need that thrust, and then we need airspeed. There might be a separate sensor or calculation for airspeed. So that's our first unique issue that might differ from other powertrains in the world. We then have our AC motor. I think many of us are familiar with this, but this is being powered by an inverter. So somewhere there's an inverter giving 3, 6, 9 phases to this AC motor. This specific example has a gearbox. It feeds a torque sensor. So we're measuring torque and speed, electrical power, battery power, thrust, and then eventually we have the propeller output where we're comparing blade pitches, blade construction, sizes to really get our full efficiency. So again, with this sort of test stand, we could have measurement of torque and speed, measurement of AC power, measurement of DC power, load cells for thrust, air movement. And this is just the powertrain components. These systems also have vibration inherent to them, so you could load this test stand with accelerometers to see how the system vibrates when things reside on a wing. It's a very important quantity. Temperature at altitude or in aircraft, temperature and reliability go hand in hand. So understanding the thermal characteristics of the motor and inverter are extremely important. And when we start adding all this together, we get a very, very complex system with a large amount of measurements. And the eDrive solution being able to take in many measurements really becomes appealing. So this is a proposed electric test stand. We've seen this in a wide number of instances. Very popular way to validate the design of the aircraft propulsion system. This system could also be taken and run back to back. So we would copy this and use it as the load machine or have a separate load machine for running a traditional dyno test. So this is a very flexible platform if you change the coupling at the output shaft. So flexibility in test stands is always important, especially at the TRL 1 to 3 levels. We need to spend our money wisely. So a test stand like this that could be used for multiple purposes might be very appealing to some people in the world. Now, once we have our awesome test stand set up and we have the picture again of an example of this test stand in the top right corner, we need to make measurements. And what type of measurements are we going to be making? And from my experience with this specific test stand, there's 3 very distinct test scenarios. One is startup and drive cycle. That's when we're turning the machine on, we're spinning it up, and we're looking at some dynamics. There's the steady state operation. This is our more steady state efficiency, and this could be at a variety of air speeds, air densities, actually quite a wide range of operation points. Some of us might think that a fan is fairly static. It's a very dynamic piece of equipment. Then failure events. The redundancy on these electric aircrafts is a very appealing quality, but at the same time, we want to understand how these systems fail. If a bird hits the prop, if something freezes up, if a phase drops, how do we handle that redundancy? So the example I have on the right-hand side, this graph, actually an excerpt from our software, uh, shows dynamic power, reactive power, and apparent power for a startup steady state and failure event. I just happen to have this great data set for the slide I made. But what we have is the machine started at 0. It spun up, and we can see the power dynamics as it's starting up is nonlinear. There are some control issues that they were having in tuning out while they were running this test. So we can see that fairly nonlinear startup performance. Then the machine's operating at speed. We're taking an efficiency value. And here we were looking at efficiency, but also endurance efficiency. So after a handful of minutes, I think it was 4 or 5 minutes, this was a fairly long test, we see this drop in power. And this was some sort of interesting event. We weren't exactly sure what would have happened. Power recovered, and then we got a big spike and a dropout. And this was a controller failure of some sort. So really interesting that we had all three of these dynamic events in one test. But at the early phases of development, it's really important to understand, how is my controller failing? How is my machine starting? And oh yeah, this plane needs to go a certain distance. What's my efficiency at a variety of loading points? Now, this test was run outdoors. You may need a chamber of some sort that can vary air density, vary airspeed to get a really proper efficiency map for your operation range. But in aircraft companies, these are things that should exist. But the important takeaways is that we need to measure and record 3, 6, 9 phase voltages and currents, make calculations, which would be power, reactive power, apparent power, possibly feed these back to an automation system. But we want to calculate, visualize, and store that data. So by calculating these points and displaying them in the real time, that gives us a really nice intuition as to what's happening in our test. We were able to watch these powers dip and do strange things in the real time, which gave the engineers intuition to shut down their test or to look at what the failure modes are. So again, one measurement system for a wide variety of events. Later in the presentation, we're going to talk about dynamic power measurement and high frequency measurement. And by the nature of us recording data, catching failure events is cooked into our DNA. We also have a wide variety of triggers where if you're just specifically searching for failure events, we can catch those as well. Now, values that we might want to calculate. Because these are complex tests, there's a lot going on. Everybody's test might be a little different based on what you're measuring, what you want to look at. So in our software, you're able to calculate your own custom equations and run them in the real time. So in this example, we were measuring thrust, we were measuring airflow, we were measuring torque, speed, our electrical signals, and we wanted to calculate the powers and the efficiencies in real time. So we were able to set airflow as a variable, set our number of cycles as a variable, because when we're averaging electrical power, as well as mechanical power, as well as propeller power, we want all those to be done on the same time frame. So we set a time frame for doing that averaging. We set some air density variables, some variables that have to do with the size of the prop. So this was a 0.3 meter prop. Input thrust, and then we run the calculations to get to our total efficiency. And in this example, it was the efficiency of the propeller. The other efficiency equations were cooked in. But we'll have more on this in later slides. But the ability to program in your own equations can be really valuable when you're doing these tests where you may have one or more variables or you may have to make assumptions. Again, these are all being calculated in real time on a digital signal processor. So they're able to be fed back to a test stand, hardware in the loop system, or an automation system. So once we've calculated these values and we've programmed them into our real time, we're recording these raw data signals for all these different pieces. We want to visualize these signals. And one of the benefits of doing calculations in the real time in the hardware is that you can visualize everything as a scope trace, or feed it back to a hardware in the loop system. So from my calculations, we had our thrust measured with a load cell. And again, from that test stand that we showed up here, we had airflow in blue. So this is the amount of air moving by the propeller. We had thrust measured in red. So this is the load cell at the back end. And from these measurements, along with our electrical power measurements, we were able to calculate the inverter power, which I have shown in purple in the middle graph. Our battery power, so that's the DC power going into the inverter, shown in aqua. And then we have that airflow power shown in red. And we end up having efficiency values for each individual element. And it's really cool to look. We have that very efficient inverter, somewhat efficient prop, and then a total efficiency of somewhere in the 50 to 60% range. But these are things that you can view as a scope trace. And if you're running an endurance test or a long-term test, you can record these values and just periodically look, see if things are changing over time. You have all the data behind these direct measurements. So it's really, really cool when you start running a test and seeing all these things coming at you as they're happening. Getting the prop efficiency, getting the prop power, the inverter power. Again, a lot of intuition for tests, especially in these early development phases. It gives us some cool options for making changes.